Okay, so now we have problem D5.5, and for this problem we know that we have the process transconductance as 400 microamperes per square volts and a threshold voltage of 0.5 volts. We also know that the minimum length of the channel is 0.18 micrometers and the maximum VGS allowed to this design is 1.8 volts. Now we need to design an NMOS transistor, right? An NMOS transistor to operate as a resistor from 250 ohms to 1 kilo ohms. So we need to define the values of VGS, so the voltage across between gate and source, and also the width of the channel. Okay, and the goal here is obtain the smallest transistor possible. Okay. So if we remember for a small VDS, okay, so for a small VDS, the curve VDS over IC, the relationship between IC and VDS is a linear curve. In this linear curve, so those blue lines that we have here, the slope of those curves, they corresponds to 1 over RDS. So 1 over RDS, which is the resistance between drain and source. Now, the thing here is that if we change the value of VGS, so basically each one of those VGS's gives us one of those linear curves. We basically change the slope of these curves. So if we increase the value of VGS, we basically decrease the value of the resistance, okay, or increase the slope of the curve. So if we have a VGS that's less than the threshold voltage, this resistance here is going to be infinite. And we can see that from this equation here, okay? Because if VGS, it becomes less than VT here in this case, basically our resistance here would be something that is negative, that's not valid. But suppose we have VGS that is equals to VT, basically this term here, right, that I have in blue here, it's going to be 0, and this one here would be like an infinite resistance. So that's the reason this first curve here is right at the VDS axis. Now if we keep increasing, suppose we pick VGS2, right, then we have a slope of 1 over 1k. If we pick VGS1, we get 1 over 250. And if we keep increasing VGS, we would probably have a curve up here that gives us another slope with a smaller resistance, until we increase VGS so much that eventually we would represent as an a short circuit, that for any value of VDS that we have, we would probably have a short circuit in the channel. Of course, there are some physical limitations in the transistor, but basically that's the behavior that we have for this curve. So in this design, we have to use this equation for the drain source resistance, which is 1 over the process transconductance times the aspect ratio. So we want to make this W and L small as possible, the smallest as possible. And we need to choose VGS here to achieve those values of resistance. Okay, so the first condition that we have is that this RDS is equals to 250, and that's equals to Kn, so Kn is 400 microampere per square volts, so it's 10 to the minus 6. Okay, just make it straight here, times the aspect ratio, times, and I'll call the overdrive voltage 1, okay, because this term here is the overdrive voltage. Now we can isolate this relationship here, right? We can isolate this one here in this equation, and then we get that the width divided by the length, the aspect ratio, times the overdrive voltage 1 should be equals to 1 over 250 times 400 micro, 10 to the minus 6. And this gives us the first condition, so the width, or the aspect ratio times the overdrive voltage 1 should be equals to 10. So that's the first condition. Now for the second resistance, we basically apply the same methodology. So we have 1K here equals to 1 over 400 times 10 to the minus 6. Again, WL, but now V overdrive 2, right? That's the second. And we can also isolate these terms here. V overdrive 2. And that should be equals to 2.5. So those are the two conditions that we have. Now, remember that the maximum VGS allowed is 1.8, right? So the maximum VGS, so let me put here, VGS max is equals to 1.8 volts. Now, V overdrive is equals to VGS minus, VGS minus the threshold voltage. This one here is fixed, right? It's 0.5 in our case. But because we need the highest value of, because this ratio here, it should be the same. It is the same on both, for both resistors, right? We can change the size of the transistor once it's manufactured, right? So we can, the variable that we have here to control the resistance is indeed VGS. Now, because here in this first condition we have the highest value of aspect ratio times the overdrive voltage, we need to use this maximum value of VGS here, because we can decrease the value of VGS to something that is less than 1.8, because that's the maximum, right? But, and in this condition here, if we decrease, we are basically decreasing this V overdrive 2 here to achieve this 2.5, and that's okay. Now, if we use this 1.8 here, we are not allowed to increase VGS to get those 10. So that's the reason we are using VGS max in this first condition here to get the aspect ratio. So if we substitute VGS 1.8 in this first equation here, so let me just point out that this is not okay, right? So if we substitute VGS here, we get an aspect ratio that it's equals to 10 divided by 1.8 VGS minus 0.5, that's the threshold voltage. So this first condition gives us that the aspect ratio L should be equals to 7.69. And from that we also know that VGS1 should be equals to 1.8 volts. Okay, so those are the two conditions, the two results that we got from the first condition. Now, because we know the aspect ratio, we can substitute the aspect ratio up here in this equation to get the overdrive voltage 2, and with that VGS2, right? So just erase this one here. So for the second condition, we know that V overdrive 2 should be equals to 2.5 divided by the aspect ratio, which is 7.69. And this gives us an overdrive voltage 2 that is equals to 0.325 volts. And this means that VGS2 is equals to that V overdrive 2, right? 0.325 plus the threshold voltage of 0.5 volts. This gives us a VGS2 that's equals to 0.825 volts. So if we select 0.825 for VGS, we get the resistance of 1K, right? A small value of VGS gives us a higher resistance. That agrees with the graphic that we had before. If we increase VGS to 1.8, we decrease the resistance and we get that 250 ohms. Okay, so now we know our range for VGS. So the answer here is that VGS, it goes from 0.825 up to 1.8 volts. But now that we have the aspect ratio, remember that the minimum length is 0.18 micrometers. So if we need an aspect ratio of 7.69, it means that the width should be 7.69 times the minimum length. And this gives us a W, so we can substitute this one here. This gives us a width of 1.3842 micrometers. And those are the two answers for this particular problem.